Welcome to week 12. We've made it. You waited this far. So, congratulations. This week is your final week of lectures. I know you're not finished yet. I know there's still a little bit to do from your assignment point of view, but it is our final week of lectures. So, well done to all of those who are still with us. Last week, we looked at abstract, interfaces, bubble sort, selection sort. So we looked at a huge amount of concepts last week, and what you need to remember, some of the concepts that we are looking at now is just to give you a foundation in programming. It's to give you an understanding. You may, at the end of this year, still not be 100% sure about abstracts, still not 100% sure about interfaces, but you know that the next time that you're in a class that someone's talking about them, or you're in a work situation where it's being discussed, you'll have the idea, you'll have the grounding, you'll know where to go, you'll have an understanding of it. And in a lot of these cases, it's only when we start working with them in kind of the real world or in earnest that we truly understand what the concepts mean. So we had a look at abstract classes, and we said that an abstract class is a class that contains 0 or more abstract methods. And remember what an abstract method is. An abstract method is a contract to say that, you know what, later on in a concrete class, a class that I can instantiate, I'm going to write the code for you. All you're doing now is you're saying you must include this method in your concrete class. So a class that has an abstract method must be declared abstract. They can't be instantiated, and they only function as a base, so they can be subclassed, and concrete classes complete the implementation. So what does that mean? So that means that if we have a hierarchy where we have animal and dog is an animal, cat is an animal, we would say that maybe animal is an abstract class. We can't create an instance of an animal. It must be a cat or it must be a dog. So those classes we deem to be our concrete classes. And in those classes, we would have all of the implementation for our methods. Okay, we looked at social network. We looked at introduction of abstract classes for post and light post, and we said that these were abstract because we wouldn't create an instance of a post. It must be a message post, a photo post, or an event post. So our abstract classes had the general information that was general to all of the classes that inherit from it. And then in our subclasses, our concrete class had the specific information that was required, that was going to allow us to create a concrete class, and we can create instances of that. So that's our social network, and you would have gone through that in your labs. If you have any questions on it, just ask in our lab session. What is an interface? We looked at interfaces, and we said that writing an interface is similar to writing a class. But a class describes the attributes and behaviours of the object, and an interface contains the behaviours that a class implements. Okay, so let's think about the abstract versus interface. An abstract class is a class that cannot be instantiated directly. It may contain abstract methods. They're the methods without implementation that we're promised that we're going to write later on, and concrete methods with implementation. So they may have methods. So you remember we have getters and setters for all of our fields. They're concrete methods. They do something. We use an abstract class when we want to provide a common base for all our subclasses and that share some common functionality between them. Interfaces are very similar. It's a contract that defines a set of methods, but it doesn't provide implementation. So classes that implement an interface must provide the implementation for the interfaces methods, unless that class, I suppose, is abstract. So we would use an interface when we want to ensure that different classes share certain behaviour, but the implementation can vary. So interfaces are great when we have multiple classes that don't share a common parent, but still need to exhibit similar behaviour. So let's say, for example, we have a class that inherits our cat class or our dog class, but actually we want to be able to save and load the data that's being stored. Well, we might create a serializer interface, and that would allow us to have save and load as methods. And all of the classes that implement that interface would have those methods in it. So our interface, what we said, it's a contract that defines a set of methods that we promise that we're going to implement at a later date. So we looked at our iMaml, and we said that in this case here, iMaml is an interface, and it has two methods, eat and travel. Neither of them have implementation. They just have our semicolon, which says that whatever class implements them is going to implement the code for them. Okay, we don't have to declare them as abstract because it's an interface. So remember the difference between an abstract method in a class or in our interface. In our class, we must declare it as being abstract. Okay, so we looked at this, our interface, and we can see here that when we went to create our mammal class and we said it implements this interface, we have to have the eat method and we have to have the travel method. So that's important. So now we know that any class that implements our iMaml will have those methods. So we're introducing good programming practice. You looked at bubble sort. So we looked at sorting, and we said sorting was when we put objects in some sort of order. So in a bubble sort, what does the bubble sort do? At the end of the first cycle through the array or the array list, whatever the data structure is, one item will be in the correct position, whatever we deem it to be, the largest or the smallest, whatever it is. And what we say, it bubbles to the end of the array or the array list, whatever our data structure is. So if we have an array of integers to be sorted increasing integer size, the largest integer should be in the highest index position of the array. So we want it to bubble up. Okay, so we'll swap each time we find one that's larger. So we'll have a look at this one here. So in this case here, we're putting it in ascending order, but we're finding the smallest, then the next smallest, then the next. So you can see here, this one is bubbling down the way. So it's sorting it by finding the smallest and swapping it each time. Now we could have done the same thing, except we go up the way and we could have found the largest and let it bubble to the top. But we're doing it so that it bubbles down. Okay, so that's where we're at the moment. So in the bubble sort, it goes through our list and the smallest or the largest, whatever it is, bubbles its way down. In our selection sort, we iterate through all the items in the array, we find the largest one, and then that is then swapped with the end of our array. So in this case here, we're going through it to find the largest one, and then we're swapping it with the last element in our array. So you can see here that we're swapping it. The next time through, we're going to populate where position 2 is at the moment. So we're going to find the next largest and we're going to put it into where number 2 is. So our selection sort iterates through all the elements of the array, selects the largest one that's stored in a temporary variable. The largest one is then swapped with the element at the end of the array. Then we reduce the size of the array by 1 and we work through the array again to find the next largest element. We put that at the end of our new array and we keep going until we get to the end. So that's our bubble sort and our selection sort, and you would have done that on Wednesday. You also looked at linear and binary searching. So before we decide on how we sort to a list, we need to decide of whether the list is sorted or not. So if it's not sorted, we just use a linear search. That means that we're going to go through every element in our list until we find the one. So if there's a million elements, we're just going to go through each one until we find it. We might find it at the start, we mightn't find it until the very, very end. But that's what a linear search is, one after another. If it's sorted, we can use a binary search. And the funny thing is, we all use binary searches when we're looking for something. And I'll get to that in a second. So this is the one that we always use because we're used to being able to, if we have a book and we want to find a page in a book, or we have an address in our address book that we want to go through. So we'll have a look at how we do that in a second. So our linear search. So we looked at the code for our linear search. And in our code for our linear search, we pass in this case, it's an array. You can change your code for an array list, the size, and what we're looking for. So in this case here, we're saying we're looping through it and we're trying to find is if this element is what we're looking for. If it is, return where it is we find it. If we get to the end and we haven't found it, then we're going to return -1, which means we didn't find it. So this is our code for a linear search. It's going through each element, one element at a time. In our binary search, if the list is sorted, we'll make use of that the same way that we search through a phone book. The binary search is such a search and it's particularly efficient. So if you've got a phone book, or even if you've got any book, I want you just to pick up a book. And if I said to you, the book has 100 pages. If I said to you, go to page 12, you would, try and find a quarter of the book. And then depending on what page you're on, if you were on page 11, you'd go forward. If you were on page 25, you'd go back and you'd look again. Okay. So when we're looking for something in a sorted array, we will try and make it smaller. So in this case here, we're going to look in a certain area and then find out if it's in that area. If it is, we're going to look in a certain area again, and again. So the overall algorithm works by always looking at the midpoint of the list. If we have found what we're looking for, great. If not, we keep going. Okay, so if not, and the value we're looking for is less than the midpoint value, then what do? We needn't look at the other side. We go to the list that's less than, and we redraw our list. If not, and the value we're looking for is greater than the midpoint value, well then using the same logic, we look to the top of the list and we forget about the other half of the list. And this was the code that you looked at for the binary search. So again, pass in the array, the size, and what you're looking for. And remember, it's ordered. So we're going to have a mid, a left. So the left, remember, is the first element, which is element 0. The right is the last element, which is whatever the size is, -1. And then we're going to start, mid is going to be halfway there. We're going to look and find out if it's what we're looking for. If it is, yay, well done. If not, then we're going to find if the number we're looking for is greater than where we are. If it is, well, now we're going to only check in the right hand side of our array the next time in. Otherwise, we're going to only check in the left hand side. And we'll keep doing that until we find what we're looking for, because it'll be the midpoint. If we don't find it, it's going to return -1. So again, you would have looked at that last week. This week, we're going to look at more collections. We're going to look at a hash set, a hash map. We're going to have a code example. And then on Wednesday, you're going to start doing some testing. Okay, so if you have any questions, throw them into Slack and we'll get back to you.